So in this video, we're going to talk about optimizing the cost of a soup can, and we're given some constraints. So it's a right circular soup can. The material for the side of the can is 1.5 cents per square inch, and the material for the lids is 2.7 cents per square inch. And we know that we want to construct a can that has a volume of 16 cubic inches. So a good way to start is to draw the picture, some kind of picture of our can. It doesn't have to be perfect. And label our variables. So for instance, I might label the radius of my can and the height, because that's what I need to figure out some equations for this can. So first off, in terms of my variables, I can come up with the volume. Volume of this right circular cylinder is pi r squared. That's the area of the base times its height. We also can come up with surface area. So now we have a top and a bottom, which are just circles. So the area of a circle is pi r squared, and we're going to multiply that by a 2 for each of them. Now we have to add in the surface area of the side. Well, to do the surface area of the side, imagine if you took the side of the can and you unrolled it, you would get a rectangle that has a height of h and a length of the circumference, which is 2 pi r. So the area of the sides is 2 pi r. Now it's not the surface area we're trying to optimize. It's actually the cost. But we're just going to modify our surface area function to get the cost, because these represent the lids. So the 2 pi r squared is getting multiplied by the 2.7 cents, and we'll do the whole thing in dollars. So 0.027, and the sides are getting multiplied by the 1.5 cents, or 0.015. Let's just do one step of simplification to get our coefficients together. So 0.054 pi r squared plus 0.030 pi r. And I am missing an h in here, and I had said it. Sorry, this 2 pi r h is from here. So let me get the h's in there. My apologies, there should have been an h there. Okay, now, next thing we're going to do is get this thing as in a single variable. Well, we were told that the volume had to be 16 cubic inches. So that's going to be equal to our pi r squared h. And what I'm going to do is I'm going to solve my constraint for h. So h equals 16 over pi r squared. Now from this, we can start to come up with a reasonable domain for r and h. Now clearly, both r and h have to be greater than 0, otherwise we have no can. Now as far as the upper limit, there's going to be some flexibility here, so you might want to go with something that makes sense. So I might notice that if r is any bigger than 4, if I plug 4 in here, I'd get 16 over 16. That'd leave me a height of 1 over pi, so way less, about a third of an inch. Seems kind of small. Similarly, I might do the same thing for h and say, okay, well h, I'm not going to let it be any bigger than 16, because the same thing happens. If h is 16, then r is no bigger than the square root of 1 over pi inches, which again is, the square root of 1/3. It's a pretty small number. So there's some variability on these upper limits. I just chose those because I wanted to deal with integers. Anything bigger than 4 won't make a very interesting can, and same thing with h. Anything bigger than 16. But if you picked something like 3 for r and 10 for your upper limit of h, that's probably going to be fine as well. Okay. Now, because we solved this for h, we can get our cost function all in terms of r. So our cost function is now going to look like 0.054 pi r squared plus, now here's where h is going to get plugged in right there, 0.030 pi r times 16 over pi r squared. And you can see there's going to be some canceling we can do. So rewriting this simplified as 0.054 pi r squared. And here I'm going to multiply the 16 and the 0.03 together. So plus 0.48. And now this is going to be over r, but I'm going to write it as r to the minus 1 because I'm about to take the derivative to find my critical points. So let's find c prime. So c prime, we're taking the derivative of this. It's just a couple of power rules. So 0.108 pi r, so that's from dropping the 2 down. Now drop the minus down, so that's minus 0.48 r to the negative 2. And we have now our derivative, which we're going to set equal to 0. Now, first thing I'm going to do is add this to the other side. So I have 0.108 pi r equals, and now instead of writing this as r to the negative 2, I'm going to have 0.48 over r squared. Because, oops, and I'm missing an r here. Jeez. Now I'm going to cross multiply my r squared to give me 0.108 pi r cubed equals 0.48. So I'm going to divide both sides by 0.108 pi. Cancel that out. 0.108 pi. And then to completely solve for r, I'm going to take the cube root or raise both sides to the 1/3 power. Okay? Now you can do this in your calculator, but it comes out to be a very long decimal. So approximately 1.12259 inches. Now we can use that to find h, because h is, we already have a relationship between the two. But first, let's determine if this is in fact a minimum. So this is our 1.12259, and let's see what would happen if we had a larger value than this. So let's use a very large value, say 3. So if I used 3 in my derivative, we'll get something very large here, large positive, and then something very small here. So I'm going to have a positive, which means c is going to be increasing. Now we don't want to use 0, but we can use something very close to 0, 0.1. So if I use a 0.1 here, that's going to make this number very small. It's going to make this number very large. So that's going to be a negative in my derivative, and we see that we do in fact have a minimum at that critical point. Last thing we need to do is find our h. We said h equals 16 over pi r squared. So subbing in what we found for r, approximately as a decimal, we'll get 4.0413 inches. So there's our dimensions that yield the can of minimum cost.